This is lecture 9 in BBSP 610. Today we'll be discussing probability. And my guess is most of you already have an intuitive understanding of probability, but today we're going to be defining probability rigorously and show how you calculate it. And we'll get into a fair amount of detail. It's honestly more detail than you probably need for the purposes of this class. And for the rest of this class, you just get the basic gist behind probability are probably fine. The reason I go into this detail is partly so that you can do the homework, but also partly just for the point of view of general scientific literacy. I remember one time when I was a kid, I was watching a weather report, and the weatherman stood up there and said, well, there's a 50% chance of rain today and a 50% chance of rain tomorrow, so there's a 100% chance of rain in the next 2 days. And as near as I could tell, he was completely serious when he said this, that he just didn't understand that you cannot get the probability of rain on one day or the other by summing the two probabilities. Over the course of today, we'll be explaining why this logic's incorrect, how you would calculate probability in this case, so that when you talk about probabilities in your own research, you make correct statements. So here's some terminology. Again, don't worry too much about the details, but I'll be using it through the rest of this discussion. First is the sample space, which is the set of all possible outcomes that we will denote by S. An event is some subset of the sample space. For example, say I randomly select a person from this class and look at their gender. Well, one possibility is that I select someone male, another possibility is they're female, another possibility, or I could consider the event they're either male or female, or I could consider the possibility that they're neither male nor female. Or say this class had letter grades and I and the event is I give a grade to someone. It could be that they get an A, which consists of one possibility, namely A, or it could be that they pass the class, which event is they get something other than F, so either A or B or C or D, or you could consider the event where the person earns at least a 2.0 GPA. They earn either an A, a B, or a C. So simplest definition of probabilities, it's a numerical quantity that expresses the likelihood of an event. In general, we'll denote the probability of a given event A by P in parentheses of A. So let's go to the coin tossing example. Let's say that we toss a single fair coin and look at whether it's heads or tails. Well, in this case, the outcome there's two possible outcomes in the sample space. There's heads and there's tails, and in this case, obviously, assuming it's a fair coin, the probability of heads is equal to the probability of tails, which is equal to 1/2. Another possibility is another scenario is that we toss two coins. In this case, there's 4 possible events in the outcome space. We could get 2 heads, a heads and a tail and a heads, or 2 tails. And to find the probability of a given event, you take the number of events, or take the number of elements of the sample space that satisfy the condition in question, divided by the total size of the sample space. So for example, to find the probability of 2 heads, well, there's one possible element of the sample space, namely heads, that consists of 2 heads, 4 total elements in the sample space. The probability in this case would be 1 out of 4. And if you wanted to calculate the probability of at least one head, well, there's 3 events in the sample, or 3 elements of the sample space that have at least one head. There's heads, heads, tails, and tails, heads. So the probability of at least one head would be 3 divided by 4. Or another example, more relevant to bench scientists perhaps, say that you're doing an experiment where you're sampling fruit flies where 30% of your Drosophila are black because of a mutation and the other 70% are gray. Well, there's two possible outcomes in your sample space, black and gray. In this case, the probability of black is 0.3 and the probability of gray is 0.7. So, the more formal definition of probability is that it's defined to be the long-term relative frequency of an event. That is, if the event were repeated an infinite number of times, the proportion, or, or if a certain random process were repeated an infinite number of times, the probability of that event, the proportion of times that event occurred would be equal to the probability of that event. So for example, if the probability of getting heads when you flip a coin is 1/2, then if you flipped a coin a large number of times, over the long run the proportion of heads would be approximately 50%. This gets a little messier if it's something like the weather, or if there's a 50% chance of rain tomorrow. What does that mean exactly, given that today will never, or given that the event, the conditions tomorrow will never be repeated exactly? Best way to think of it is that on conditions similar to the conditions tomorrow we'll get rain about 50% of the time. There's other ways to define probability, but that's way beyond the scope of this class. So, certain rules about probability that hopefully you've seen some point earlier in your life is that probabilities always have to be between 0 and 1. That makes sense. If it's a long-term relative frequency, an event can't happen more than 100% of the time or less than 0% of the time. The probability of the sample space is 1 because all possible outcomes are contained in the sample space. Now some terminology. Two events are disjoint if they cannot happen at the same time. So two examples of disjoint events are heads and tails. If you flip a coin, it can't land both heads or tails. It's going to be one or the other. Likewise, if I select a person from the class, they can't be both male and female. On the other hand, there are some events that are not disjoint. If you're being treated by cancer, you could be treated with surgery or chemotherapy, or you could be treated with both surgery and chemotherapy. Or if you're vaccinated to a disease, you may be exposed to the disease. Vaccination may hopefully prevent you from getting the disease, but doesn't mean you'll never be exposed to the disease. The reason why we define disjoint events is for our first probability rule, which is that if A and B are disjoint events, then the probability that A or B occurs is equal to the probability of A plus the probability of B. As I said, this only works if the events are disjoint, and this is where the weatherman got it wrong. It's possible that it could rain tomorrow and rain the day after tomorrow. So you can't just take the probability of rain tomorrow plus the probability of the rain after tomorrow to get the probability of rain on either day, because the events are not disjoint. Let's look at an example where they are disjoint. Going back to the grades example, say 30% of the class gets A's, 30% gets B's, 20% gets C's, 10% get D, and 10% get F. And you'll never get more than one grade in a class. These events are disjoint. So if you want to find the probability that a person passes the class, which is the probability of A or B or C or D, that's just the sum of the individual's probabilities. The probability of A plus the probability of B plus the probability of C plus the probability of D, which is 0.9 in this case. Similarly, the probability of a 2.0 or higher is the probability of A plus the probability of B plus the probability of C, which in this case is 0.8. Next piece of terminology is independent events, which are events such that if you know the outcome of one event, that doesn't tell you anything about the probability that the other event occurs. And this is not the same thing as disjoint, because in fact disjoint events are never independent. If I flip a coin once and the event 1 is getting a heads, event 2 is getting a tails, those two events are disjoint, but they're not independent, because if I get heads, I know I didn't get tails, and likewise if I get tails, I know I didn't get heads. On the other hand, if I flip the coin twice, the result of the first toss is independent of the result of the second toss. So two examples of events that are not independent is, for example, gender and prostate cancer. It's safe to say that if you're female, the probability of prostate cancer is 0. Similarly, if smoking and lung cancer are not independent, if you smoke, the probability of lung cancer is greatly increased. And if you remember the example I gave in the first lecture in class on how children with larger feet tended to have higher test scores because both shoe size and test scores are associated with age. So in this particular case, shoe size and test scores are not independent. Now just because two things are not independent doesn't mean that they cause one another. We know that shoe size doesn't cause higher test scores, but these two variables are still not independent of one another. A few examples of events that are independent, presumably, is that, as I said before, if you flip a coin twice, heads on the first toss is independent of heads on the second toss. Or, presumably there should be no association between how old you are and what your blood type is. Or, final example that sometimes makes people a little skeptical and in some cases upset when I bring it up is, say a basketball player hits 8 shots in a row. Is he more likely to make his next shot? Now, if you ever watch basketball on TV, the announcer is probably likely to say, "Oh, LeBron James has hit 8 shots in a row. He's hot right now. They need to make sure they get him the ball." Well, in fact, I believe it was the Philadelphia 76ers one year actually collected detailed data on this and looked at the probability that a given player makes a shot given that he made his last several shots or missed his last several shots, and it made no difference whatsoever. The probability of making a shot just does not vary much over the course of the game or over the course of a season. And to this day, I have some friends who are statisticians that are skeptical of that finding, but that's what the data indicates right now. Some cases, it's unclear if two events are independent. Is watching violence on TV associated with committing acts of violence in real life? It's a difficult hypothesis to test. And right now I'm skeptical of that association, but I'll say that the jury is still out. Another possibility, say you're doing a genetic study of some genetic disease and you want, and is that disease associated with a missing value for a particular SNP? Well, it's possible that they're completely independent and that the genotyping errors are completely random. On the other hand, maybe the SNP is in fact associated with the disease, and maybe the minor allele, or the major allele for that matter, is more likely to be missing than the other allele because it gets genotyped less readily or something like that. In that case, the disease and missingness may actually be associated. At any rate, the reason we care about independent events is because if two events A and B are independent, then the probability that A and B both occur is the probability of A times the probability of B. So, simple coin tossing example, if A is you get heads on the first toss and B means you get heads on the second toss, the probability of both A and B is equal to 0.5 times 0.5, which is 0.25, consistent with what we got earlier in the lecture when we just divided the number with two heads by the size of the outcome space. Now, a slightly more complicated example. Let's look at blood types in the United States. This table shows the approximate distribution of blood types. About 38.4% of the U.S. population has O positive blood, about 32.3% have A positive, about 7.7% has O negative, etc., etc. So let's use this table to calculate certain probabilities, and let's verify these probabilities or what our rules say that they should be. So let's find the probability that a person has type O blood. Well, a person can't have both Rh positive and Rh negative blood at the same time. So the probability of having type O blood should be equal to the probability of O positive plus the probability of O negative, which is 0.384 plus 0.77, which is equal to 0.461 as it should be. Two other possible disjoint events are that what's the probability of having either Rh positive blood or Rh negative blood? Well, that's equal to the probability of being Rh positive plus the probability of Rh negative, which is 0.833 plus 0.167, which is equal to 1, which agrees with our intuition. Everyone is either positive or negative, so that probability should be equal to 1. And if you want to find the probability that you don't have type O blood, you can use something that's called the complement rule, which takes advantage of the fact that all probabilities have to sum up to 1. So the first way that we can find the probability that a person does not have O positive blood is just to sum up all the individual outcomes that make up that particular event. So the probability of not having type O blood is the probability of type A plus the probability of type B plus the probability of A and B, which would be 0.388 plus 0.111 plus 0.04, which is 0.539. And when you have only 4 possible outcomes, that's easy enough to do, but in some cases there may be a longer list of possible outcomes and you may not want to do all that math, but there's a shortcut that we can take. Since the probability of O or not O has to be equal to 1, and since those are two disjoint events, we know that the probability of O plus the probability of not O is equal to 1, so in other words, the probability of not O is equal to 1 minus the probability of O, which in this case is 1 minus 0.461, which is 0.539, consistent with what we got when we did it the other way. And one more example of disjoint events, say you wanted to find the probability of type B blood or type O blood, well, you can just take the probability of type B plus the probability of type O, which is 0.461 plus 0.111, that gets 0.572. Now let's use the rule about independence. Rh factor and blood type are independent, so if we want to find the probability that someone's O positive, that's the probability that they're type O and that they're positive. Since they're independent, that should just be equal to the probability of being type O times the probability of being Rh positive, which is 0.461 times 0.833, which is approximately equal to 0.384 after rounding. And we could also use this if we have two people who are not related to one another and you want to find probabilities of their two blood types together. Let's say, what's the probability in a given couple that the husband is type A and the wife is type B? Well, that would be equal to 0.388, the probability of the husband being type A times the probability of the wife is type B, which is 0.11, and ends up being 0.043. And we can take this even a step further, which is, what's the probability that one spouse is type A and the other is type B? Well, we can write that event as the probability the husband is type A and the wife is type B, or the wife is type A and the husband is type B. Using the same logic as we used on the previous slide, either of those probabilities is equal to 0.043, so we sum them together. The probability of one spouse being type A and the other being type B is 0.086. But once again, this only works if the events are disjoint. If, say, we wanted to find the probability of being type O or Rh positive, if you just naively sum up the events, you get 0.1294, or get 1.294, which is obviously impossible. This is the mistake that the weatherman made. So, if two events are not disjoint, then you can't find the probability of both events simultaneously, or find the probability of event A or B by summing together the individual events. What do you do in that case? Well, I'll show you on the next slide. You can use what's called the general addition rule that works regardless of whether the two events are disjoint, which is that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This picture here might help you understand where this formula came from. The idea is that if you want to find the probability that you're in either the green bubble or the blue bubble, you can take the area of the green bubble plus the area of the blue bubble minus the area that's in both bubbles, because the area that's in both bubbles gets counted twice. So to use the general addition rule, in the previous example, the probability of being O or Rh positive is the probability of being type O plus the probability of being Rh positive minus the probability of being O positive. So that's 0.461 plus 0.833 minus 0.384, which turns out to be 0.91, which seems more reasonable. Next, we'll define something called conditional probability, which is the event, which the intuition behind is, say you want to find the probability of event B given that event A has already happened. What's the probability that your the second coin toss is ahead given that the first coin toss is ahead? And in general, the way you compute that is the probability of A and B divided by the probability of A. So, for example, let's say that we flip two coins and define the following events. Event A is the first flip is ahead, event B is the second flip is ahead, event C is that at least one of the two flips is ahead. So the probability of A is clearly equal to the probability of B, which is equal to 1/2. Probability of C, at least one flip is ahead, that's equivalent to the event that the first flip is ahead or the second flip is ahead. So we can calculate that by using the general addition rule again, probability of A plus the probability of B minus the probability of A and B. Well, since A and B are independent, the probability of A and B is just 0.5 times 0.5. What's 0.5 plus 0.5 minus 0.5 times 0.5, which turns out to be 0.75. So if you assume that the probability of rain tomorrow is independent of the probability of rain the day after tomorrow, which is a big assumption that's probably not true in practice, but if you assume that's the case, then the probability that we get rain either tomorrow or the day after tomorrow should be 0.75, not 1. What if we wanted to calculate the probability that, say we know at least one flip was ahead, what's the probability that the first flip was ahead? Well, in that case, we can use the conditional probability rule. We want to find the probability the first flip is ahead, given that at least one of the two flips are ahead. So, using the conditional probability formula, we want to find the probability that the first flip is ahead and there's at least one flip divided by the probability that at least one flip was ahead. Well, the probability of at least one head and the probability the first one is ahead is just equal to the probability that the first one's ahead, because if the first one's ahead, then of course there has to be at least one head. So it ends up being the probability that the first one's ahead divided by the probability that at least one was ahead, which turns out to be 2/3. So let's do this with the blood type example. Let's say we know that a person is Rh positive. We want to find the probability that they have type A blood. That's the probability of being A positive. A and Rh positive divided by the probability of being Rh positive, which is 0.323 divided by 0.833, which is 0.388, which is just the probability of being type A in the first place. And that's what we expect, that blood type and Rh factor are independent. The probability of having type A blood, given that you're Rh positive, should just be equal to the probability of having type A blood generally, which is what we observe here. And the rule on this slide shows that this isn't a coincidence, that two events are independent if both have positive probability. The probability of B given A is just equal to the probability of B. In other words, knowing that A has happened doesn't tell you anything about the probability of B, which is the definition of independence. So that brings us to what's known as the general multiplication rule, that if you want to find the probability of A and B, even if A and B are not independent, you can calculate that as the probability of B given A times the probability of A. Oftentimes, the probability of B given A is easier to calculate than the probability of A and B. Oh, one final example for this lecture is what's known as the Monty Hall problem. It's kind of a fun one. It's good for confusing people at parties and so forth. I've given this example to some really smart people who sit there and tear their hair out. It's like, Eric, this can't possibly be right. That's insane. That makes no sense. But I'll work through the probability and see if I can convince you by the end. If you're not familiar with the Monty Hall problem, it gets its name from an old game show called Let's Make a Deal. Monty Hall was the host of this particular game show. And the way this game show worked is that you were allowed to pick one of three doors. Behind one of the doors was a car. Behind the two other doors were goats. And obviously, your objective here is to try to get the car. So, on face, you have a 1 in 3 chance of picking the door with the car. However, after you pick a door, then the host opens one of the other two doors and shows that there's a goat behind it. Then you have the option of either staying with the door that you originally chose or switching to the other door. So the question is, should the contestant switch to the other door? And most people's intuition is, well, it doesn't matter. There's a 50-50 chance of getting the car either way. So so should she switch? Well, let's work through the probability here. If the contestant doesn't switch, the probability that she wins the car is 1 out of 3. She only gets the car if she got lucky enough to choose the door with the car the first time. But to illustrate how the probability works, let's just assume, without loss of generality, that the contestant picked the first door. And let's also say that the host opens the third door after she picked the first door, and let's let Ci denote the event that the car is behind door I. Well, So first of all, let's calculate the probability that the host opens the third door in the first place. Well, you can do that in terms of conditional probability. It's the probability the host opens the third door is equal to the probability that the host opens the third door given the car is behind door 1 times the probability the car is behind door 1 plus the probability that the host opens third door given the car is behind door 2 times the probability the car is behind door 2 plus likewise the probability the host opens door 3 given the car is behind door 3 times the probability that the car is behind door 3. So and that's equal to 1/2 if the car is behind door 1, then the host has a 50-50 chance of opening door 3 because he'll open either door 3 or door 2. If the car is behind door 3, or if the car is behind door 2, then he'll open door 3 with probability 1 because he will never open door 2 because it has the car behind it. And similarly, if the car is behind door 3, he'll never open door 3 because it has the car behind it. So you sum up those probabilities, it ends up being 1/2. So let's find the probability that the car is behind door 2 given that the host opens door 3. Well, that's equal to the probability that the car is behind door 2 and the host opens door 3 divided by the probability the host opens door 3. We've already calculated the probability the host opens door 3, but what's the probability that the car is behind door 2 and the host opens door 3? Well, that's equal to the probability that the host opens door 3 given the car is behind door 2 times the probability the car is behind door 2. So work out all those probabilities, you find that the probability the car is behind door 2 given the host opens door 3 is 2 out of 3. So in other words, if you switch doors, you double your chances of winning. If you didn't follow all that math there, you're just having trouble wrapping your brain around it, here's a graphic that might make it a little easier to see. That say that, trying to remember how this graphic works, say if the car is behind door 1 and the host can either open door 2 or door 3. If you stay, you get the car. If you switch, you get the goat. However, if the car is behind either door 2 or door 3, then if you stay, you get the goat, and if you switch, you get the car. So, yeah, like I said, fun example of probability that you can use to mess with people at parties. The main things to remember from today's lecture is that the probability of an event is the frequency that the event will occur if it's repeated infinitely many times. You can compute more complicated probabilities when you use certain rules, and when you apply these rules, make sure that the assumptions about events being independent or events being disjoint are satisfied. If they're not satisfied, you can end up with nonsensical statements like 100% chance of rain in the next 2 days because 50% chance tomorrow and 50% the day after tomorrow.